Unit 4B will be a continuation of our discussion of energy, where we'll talk about a few new types of energy, like spring energy, thermal energy, chemical energy, and a new diagrammatic model called system schemas. So think back to our previous discussion about energy. We learned about kinetic and gravitational energy, but now we're going to introduce a few more types, like spring energy, thermal energy, and chemical energy. Spring energy is the energy that's stored up in some type of elastic object based on how we compress it or how we elongate it. So we can take an example of this object at its equilibrium position attached to a spring. We see that if we pull on that object to the right, we would need to demonstrate a spring force to do that. And therefore we have a force acting over a distance, and we are doing some work. This work manifests as a spring energy, and the equation for the spring energy is 1/2 kx squared, where k is the spring constant that tells you how rigid or loose a spring is, and delta x is the displacement from the equilibrium position, so however much we displaced it from its resting point is going to be delta x. Sometimes this will be called elastic energy. Thermal energy is the internal energy of a system, which is often associated with random motion of the particles within our system. So the more we heat up an object, the more the particles and atoms in that object will vibrate with heat energy. Often thermal energy is associated with the temperature of a system. And usually you'll see thermal energy coming up in our class when we have friction acting or air resistance. So the more that we experience friction, the hotter an object gets. Therefore, it's gaining thermal energy. And that thermal energy is given off to the surroundings or the object. Thermal energy is the internal energy of a system, which is often associated with random motion of particles in that system. So the more that we heat an object up, the more that its atoms inside of that object will vibrate with some heat. Thermal energy ends up coming up in cases where we experience friction or air resistance. And this friction causes the temperature of an object to rise, and that heat energy is given off either to the surroundings or stored up in the object. So for example, if we have a person pushing a box along the ground, there will be friction between the box and the ground, and that'll cause heat to be generated. Chemical energy is the energy associated with the bonds in a material. And so chemical energy will come up in cases where we are undergoing some kind of chemical process. Some examples where you might see this in our class is in metabolism, where you eat some breakfast in the morning, you store up some chemical energy, and then maybe you go for a run and turn that chemical energy into kinetic energy. Or in the case of combustion in your car's engine, where we have chemical energy stored up in the gasoline of your car, and then it is burned in order to convert that chemical energy into some other type of useful work. Another case might be in photosynthesis, where plants take in sunlight and store up chemical energy so that they can undergo biological processes. One of the most common cases where we'll see chemical energy come up is in exercise or in the basal metabolic rate of humans. We're taking food energy in, and that food energy is used to do some work. Maybe you want to go lift some weights in the gym, and that would be useful work that we get from our chemical energy. But also our body just gives off body heat, and that is thermal energy that's given off to the surroundings. Or we can store up this food energy for later use by creating fat in our body. And now let's revisit our conversation about the conservation of energy, which means that the total amount of energy in the beginning will always equal the total amount of energy in the end, as long as we're dealing with a closed system. That means no external forces are coming in from some outside object. Remember, the conservation of energy equation says that the total amount of energy in the beginning will equal the total amount of energy in the end for any type of physical process. So if we take a look at this example where we have a rock that we raise up to some height, we would impart gravitational energy onto it by doing that. And if we let go of the rock, its gravitational energy will convert to kinetic energy. And then when it comes in contact with this spring, it will compress that spring and store that energy as spring energy. And then the spring can decompress and send the rock back upward, giving it kinetic or gravitational energy. But now in our conservation of energy equation, we need to consider more than just kinetic and gravitational energy. We'll also need to consider these new types like spring energy, thermal energy, chemical energy. And if you don't know what to call some form of energy, you know it went somewhere, but you're not sure what to call it, you can just call it other energy at this point. There are other types of energy that we'll deal with in physics class. One case where you might see other energy coming up is if we take that spring out of this situation, we raise our rock up to some height, giving it gravitational energy, we drop it, it gains kinetic energy, but then when it hits the ground, it stops moving, and it's at zero height. So it doesn't have kinetic energy, it's gravitational energy. It definitely doesn't have spring energy. There's no chemical energy being stored up in any bonds of any material, but there might be some heat that's generated. So we would call that thermal energy. Or if we deform the ground or create some sound when the objects clash, then we could call that other energy, because we don't quite know exactly what to call that. A few other terms that might come up in our conversation about energy are efficiency. Efficiency tells you how much useful work you get out from how much energy that you put in. And we use the letter eta, the Greek letter eta, which looks like a cursive N, to denote the efficiency. Our equation for efficiency involves the amount of useful energy or work that we get out of a process divided by the amount of energy that we put in. So often we'll say the work out divided by the energy that we put in will be our efficiency. And we would have units of joules for work and units of joules for energy. And so we have joules over joules, those cancel, and that means that efficiency is a unitless quantity. It doesn't have any units associated with it. It's a percentage. So the efficiency of some standard processes that you may have heard of before are like in solar cells, where we take in light energy and generate electrical energy. Solar cells are about 10% efficient. A lot of that sunlight that comes in is given off as heat, and we can't get that back for useful work. We can contrast that with coal power plants, which is how most power is generated in our society. We burn up coal, we retrieve the chemical energy from that process, and use it to power our devices. Coal power plants have about 42% efficiency. We can also look at some physiological processes like bicycling. Bicycling, you put some energy in and it moves you forward and does some work, and we get about 20% efficiency for the process of cycling. We can contrast that with swimming, which is a lot harder. You have to put a lot more work in, a lot more energy in to get the same amount of work out. And so swimming is estimated to have about a 2% efficiency. The other useful term that we'll need to talk about is power. Power is the rate at which work is done, or how energy is expended. Since it's a rate, we're talking about relating energy to time. So the equation for power involves either work divided by time or energy divided by time. And that means that we'll have units of joules over seconds. We call this unit, a joule over a second, a watt, and that is the standard unit for power. And you might see watts come up in light bulbs, for example. You have a 60-watt light bulb. Our final diagrammatic model for the energy unit is called a system schema, which will outline all of the objects that are relevant to the situation and all the forces acting between them. A system schema feels a lot like an interaction diagram. It's basically just an interaction diagram that's expanded to include multiple objects rather than just focusing on one object within your system. So if we think back to the example of the rock bouncing on the spring, we can draw a system schema for this situation, which will talk about all the objects and all of the forces that are relevant to the scenario. To draw a system schema, first you draw all of your objects in boxes. So I'm going to draw the rock, earth, and the spring in a box. Then you draw all relevant forces that are acting between all objects as an arrow between those two objects, and this arrow should have a head on each end representing an action-reaction pair from Newton's third law. And so in this situation, we would have a force of gravity that acts between the earth and the rock, and we'd also have a spring force that acts between the spring and the rock. And for any forces that are only acting for a temporary amount of time, this rock is not always feeling a spring force, we want to draw those arrows as a dashed arrow, saying that this rock is only in contact with the spring for a temporary amount of time. But gravity is always acting on the rock, so we draw that as a solid arrow. Then you designate your system. You can choose which objects to include in your system by drawing a dashed line around all the objects that you want to include. And for a closed system where we don't have any external forces acting, we would include all of the relevant objects in our system. But you can change this around and choose to include certain objects in your system, and that would end up giving us a system where maybe energy is not conserved because it's open to the environment and external objects can act with external forces. Finally, you'll want to list any assumptions that you made when drawing this system schema as a footnote at the bottom of the diagram. So for example, I listed that this spring in this situation was assumed to be massless, and that's why there's not a force of gravity acting between Earth and the spring. So any simplifications that you make, you'll want to include as an assumption down at the bottom. And so now we have 3 diagrammatic models for our energy unit. We have the system state diagram, we have the energy bar charts, and we have the system schemas, and these all work together to tell the full story about energy. That'll cover everything for Unit 4B. I'll see you in the next one.